Okay, so this is me here. And here this would be the Blender rendered result. Actually, probably not that necessary to render it so accurately because I don't have any fancy texture seeds or anything like that. I think there was a lot of stuff. And actually, those are all small, right? We have to go to complex motion. Have you done the demo of your assignment one for complex motion planning career? Okay. Then you still have to do that today. Yeah. But didn't Leo type something today? The PA514 Java, find me on the fifth floor. And I wanted to, yeah. So let's see. Capture audio. No, that's the wrong. Capture audio. I know. Blender has a. No, no, no. It has the wrong. Okay. Yeah. And now one thing that I wanted to try and do is camera track. So animation is yeah, yeah, sure, but I want to. This is not something you would remember unless you do it every day. So let's just try and move the camera forward. This local select. Here. Keyframe breakdown extreme jitter. Easing. Oh my gosh. Yeah, I have the keyframe already. And 40, I can go grab. Z, X, 0.3. Ah, negative 0. No. Grab X, negative 0.3, brings it forward, and then rotate Z 10 degrees, 15 degrees. Okay, then I can insert a keyframe there. Okay, then I'm gonna grab and go local X maybe. Oh. Alright. Alright. Go to 80. Rotate Z minus 80. Okay, so now my camera moves. And let's just make 250 frames. Rotate that 45. Okay. So then we can render the animation. That would be a little bit slow. I think maybe I can reduce the size of that. Oh, it's frame one. Okay. Yeah. I can set the render settings to be less than that. Because we don't need to render at such high resolution. So where's the view? settings, view, message, render was used. So there's a way to the thing. The window. What's that? Vertical split. Yeah, about the output. And then here, horizontal split. Here, one property. So here you can set up your environment, then where's the render? Not yet. No. Ah, yes, yes. There's the render. Yeah, that's true. Here. So let's make it 320 plus 240, just so that it runs faster. And then let's see. Then render. The menu bar is off. It's weird. I think it's because it's on the top here, usually. But video sequencer. Horizontal split. Channels. Okay, that just renders one frame. maybe I should have picked it. Okay, that's actually okay. What I wanted to do was, if we have this kind of environment, right, then basically it's a 2.5D environment. Right? You can look at it from the top down, right? And this would be the issue for a robot to navigate through that kind of world. So, one thing that we can do, that I want to do for later on, is I want to position a camera there. Here's um, a camera, and then bring that camera to the center of our world. Ah, yeah, it's because it was on the channels. Then move it by 5, so that should be 5 meters, 4 meters, and 2 meters, sure. Now I want to rotate it Z at 90, and I want to move it to the right. So scale 0.5. camera here. If I then set that as the active camera. Bring it up higher. And then we can see that kind of environment. Then we can increase the focal, decrease it. Then how do you want, what kind of algorithm would you propose to deal with this kind of environment for path planning? Now we looked at, first assignment, we did discretizations of the world, right? And we also looked at the rapidly exploring random tree algorithm, which is a probabilistic algorithm. But in this kind of environment, then both of those approaches have some inefficiencies, right? Because basically, if we're discretizing it, then we don't know how big we can make our cells, like what the minimum size is that we need to keep track of to make sure that the robot can still fit through. On the other hand, the rapidly exploring random tree algorithm works quite well, but it has issues in that it often includes unnecessary motions, so, or in particular oscillating behavior that you need to post-process your path and um, check this stuff. You need to post-process it. So one other approach that we can use is cell decomposition. If you have an environment like this, then what you, and if you know that this is your map and you want to plan a path through there, then of course discretization would not be very efficient because I need to be able to pass through here, right? So that means that if I want to do a search through there, my maximum size that I can use for an area would be determined by this distance here of the obstacle clearances, basically, right? I cannot possibly make the discretization larger than that because otherwise it's just going to map it and say, oh, there's an obstacle in the path. On the other hand, if we're up here and I need to make a small decomposition like that, then I actually may do a lot of exploration of this environment with a small discretization. So the idea would be that we want to develop an algorithm that allows us to sort of vary the way that we map the environment, that keeps track not just of the clear path, but also how much empty space is around us so that we can speed it up. So let me take a screenshot of that. Actually, I can render this. And one algorithm that I like for solving these kind of problems is quadratic decomposition. So let's have a look at that one. Where complex model. Which one is make a copy? This one? Need to drive. Hey, how come? Oh, now it puts a Chinese copy there. see that it's shared. Anyone was doing. So cell decomposition. Try to sort of avoid the main issue with search-based approaches by allowing us to adapt the size of the discretization, the size of the cell that we search through. Now, that is crucially important because as a search process, you can expect, or the runtime cost usually grows exponentially with the number of cells that you need to move through in order to move from the initial state to the goal. So the more cells you have in your path, exponentially, the more expensive your path planning becomes. And how do you think cell decompositions can adapt to the environment? Like, what would be the crucial feature for determining the size of a cell? If we look at the image here that I just took, then I think we all agree that here we want to have a large cell, right? And here we want some smaller cells. And maybe here we want some medium-sized cells. But why? Right? And what do we mean by more complex in this case?
If you have more space to move, but it's not flat space like in the middle. Like
no, this is all flat here. There's no, I mean, it's just a 2D plane. Right?
Yeah.
It's not going uphill or downhill.
I think it's like you have more corner.
Not corners, we have more obstacles, right?
Yeah.
So our cell decomposition should be based on the obstacles, the distance that we have to the obstacles. Now, there is different types of cell decompositions that people have proposed, trapezoidal ones, where you try to break up, by cell decomposition, we break up the environment into different parts. So you break it up into sort of like four-corner pieces, right? Slices through the environment. And we can see that here, for example. Like here, if I wanted to take this space and I want to represent it, then I would end up with this kind of shape, a trapezoidal shape, if I wanted to match that exactly. And then here, you can sort of see, here we would get a rectangle. There, right? Because it just happened to be aligned with the boundary, but it usually is not the case like that. So, okay, but dealing with these trapezoids is not so easy computationally, right? You need to represent them, and that you need to calculate angles, the intersection with lines that are going at an angle. So instead, quadtree decomposition is a pretty clever algorithm where our basic shape for the decomposition is always a square. And squares are much easier to deal with than with trapezoids.
Sounds like
Huh?
three-dimensional shape.
Yes, it is a similar to that idea. The algorithm is actually pretty easily explained. So we split the environment into 4 quadrants. Top left, top right, bottom left, bottom right, which is where the quad is Latin for 4, so that's where the 4 comes from, the quadtree decomposition. We take the environment and we split it into 4 quadrants, like that. And then we check if a cell is completely free, which means no obstacle, then we mark the entire cell as free. If a cell is completely covered by an obstacle, then what do we do? Yeah. So then what's the only thing left? Yeah. If a cell is mixed, then we apply the algorithm recursively. And that's almost the entire algorithm except
We use the key to outline the process instead of recursively.
you can, usually if you implement it, you would implement it with a queue. People usually do that for computational efficiency. In this case, I don't think it makes that much of a difference because your branching factor is constant. It's always 4 children that you're going to get. So your recursive stack is not going to grow to very different levels. But yes, of course, you can use a stack or a queue. The only thing that's left is for every recursive algorithm, you must have what? You must have a stopping criteria. You must stop your recursion at some level, right? So we haven't said that yet, but it's pretty obvious what we do is if a cell is minimum size, then if a mixed cell then we give up, then we mark it as obstacle instead of splitting it. Because otherwise, if I have a line that goes through and I'm trying to put squares there, it will be tiny, tiny squares, right? They'd have to be infinitely small to match a line if it's not aligned with the axis of the environment. So at that point, then we just give up. Say, okay, fine. you win. Right? But that's the entire algorithm. So if you look at this particular image here, then here we would have, this would be very good for quadtree decomposition algorithm. I would just mark that as free, right? Here I'm mixed because I have an obstacle, but I also have some free space. So we would split it into 4 components. Then I have a free space here. This one would be split. Then these ones we would split. This one would be split then. And this one as well. And here we would get some free cells. Right? So implement the quadtree decomposition algorithm for a simple environment like that. Now, originally I wanted to just use Blender to get the environment that we drew, but that may not be so easy because of the lights and the shadows that I added. I think I got a little bit too carried away with Blender and added too many lights and too much reflection. But so it will be non-trivial to read that in and get all the obstacles, the blue ones. Like I'm not sure if I can detect blue from the black here.
Now there's a the shadows because you have to distinguish those shadows from the black one.
Yeah, okay. The shadows, I think they will be black. I think that's okay. Yeah. I'm more worried about detecting this one as what the yellow stepping obstacle. Oh.
Because if the output is a material, then the color of it will red.
Yes, in reality, that poses a problem. From this viewpoint, it wouldn't, because if you look, the shadow here is actually black, so that's okay. Actually, I think I made a mistake because no cycles.
Yeah, because in my case, the shadows are really the output themselves.
Oh, yeah. Oh, you have a huge light there. Yeah, more spotlight. Yeah.
So,
But that's okay. You don't want your robot to walk that close to the obstacle anyway.
so it doesn't walk around.
Yeah, yeah. So let's try and generate an environment. And here, what did I say was uh, three, 3 by 6, 3 by 4 meters. And I want to generate some obstacles. Um, let's say, so let's change the angle to 1, and then a length. Um, Three hundred to so let's plot that. Set axis off. I thought it was axis off. Okay, then So we draw the environment. Uh, 1, 0. So here's our environment now. I'm not sure why my lines are all so long. Shorter ones. Oh, 3 meters to 20 meters. That's fine. 30 to 200. Right, so here we have an environment now with some wall obstacles, just a few walls. Directly use that one because I would have to extract the lines from here, from the image, right? Because I need to, when I split it into 4 quadrants, I need to check if there is any obstacle in there. So with the render, I could go and say, oh, is there anything non-black here? But the problem is, here I probably don't recognize, I'm not sure if I'll be able to distinguish this from this so easily, just looking at the brightness. Even though for humans the color makes perfect sense, it's not so easy on the computer. So that's just why I generate the environment randomly right now. But you can implement, of course, one that renders the render environment. The other thing is I would have to, do I still have the picture? Yeah. I mean, we can try it if you want. The blender part is more interesting for the animation. Like you can make the camera move, pan around, so you can pretend the robot is driving through it. And then you can look at the images. You can look at the images that you would get from the robot. Right? But, well, okay, if you want to, I can take this and dot open, and that should be environment dot. Okay, so here's our image, and then image one, where image one, less than 90 is equal to let's see what that is. Convert it to a NumPy array first. 5469114. Okay, so this is our thresholding now. And you can see the problem is the lights here. And they will be set to 255. So if I go 128, then what do I get? Oh, okay. Now great, right? Now our fluorescent lights, our light is gone, but of course my walls are gone too. See, I told you we shouldn't be doing this. Okay, now it sort of is okay. 110, 100, no, 1C. 105. It's always a dumb idea to use colors. Okay, see like 103. Now I can try 102. And then, of course, if anything, if somebody opens the blinds, then it would be disaster. Okay, I'll stick with 105. Okay, fine. So you want to implement pottery decomposition for this, then go ahead. Now you have it. One thing is, I'm not sure why. What does it count as black and white? Okay, so here's your environment. Now you can see, I think we're missing already one blue wall here. So 105 isn't, and we're missing a wall here, but okay, fine. That's why I didn't want to do this.
But in real case, these conditions will
No, because in the real case, I don't care about the top level view, right?
Yeah,
I only care about the view from the robot. This was only to show the quadtree decomposition algorithm. So this doesn't really.
how we can find the project condition
By driving a little bit, building a map where you draw the map like this, so you detect the blue wall, then you put the blue wall into the environment. Then you can apply your quadtree decomposition algorithm afterwards. Right? So I think we better stick with this one. It also gives us some more interesting environments. You can certainly apply the algorithm here to this environment as well. Actually, oh, yeah, I forgot about that too. That was brutal. I remember converting a figure into RGB was actually also not so easy. What did I have to do that? Ah, you draw it as a canvas. When did I do that? So here I want to implement the quadtree decomposition algorithm for the environment. Let's stick with this. It'll look a little bit more interesting. Then afterwards we can apply it to here. So height, width, obstacles, blah, blah, blah. So now, what do we do first?
because
What's the size of the square to start with? Yeah, just split, right? In order to be able to split it, I need to know the coordinates of the point that's in the center, right? So here, actually, I don't think environment will work just yet because, yeah, because I only have height and width for the environment, but when I actually look at the top left, it's going to work, right? Because it's from 0 to half of the width, half of the height. But if I move to the top right, then it's going to be y coordinate is going to be 0 to height over 2. But the x coordinate is going to be width over 2 to width. So if I only pass height and width of my environments, then I would have to change the coordinates of all the obstacles, which would be annoying, or I have to pass in this offset for where the cell starts. Right? So I'll set it to none, and what did it say? If the cell is none, then it's 0, 0 height over width. Can I work with that? Okay, I guess. Yeah. Yep. Okay. And I passed in the environment. Height with obstacles in the environment. This needs to go first. Here's the height and the width. And if I don't have a cell, we set it for everything. So then I can do that. Yeah. I can split it up, and cell 3 equals true. Okay. That also will work. Cell obstacle is full. Okay, now you're just making stuff up. I could do the check there, but I can just call the quadtree and then have the check on the entire environment. What I need to know now is if any of the lines are crossing this cell, right? So, for obstacle in obstacles, yeah, and split it up. Now, when I draw it, it was insistent on changing to this, which is dumb in a sense. X4, what's X4 now? X2 minus, and now this is also dumb. So the line goes from X2, Y2 to X3, Y3. That's what I'm drawing to, right? Yeah. So X and Y will be the center of the obstacle. And here we have X2, Y2. So now, how do I test if that line is inside of my environment? inside of my cell, and the cell goes from, this doesn't work either, there should be cell X, cell Y, cell H, cell width. So the line will be, now we have to consider the different possibilities, right? Basically, I have a cell, right? And that cell has coordinates CH, CX, CY, and CX plus width, C width, CH plus CY plus CH. And now, for my line to be able to detect if it's inside of this particular cell, I need to do a couple of tests. One would be if any line starts and crosses one of the boundaries. Right? In that case, clearly there will be an obstacle in there. Right? So we have to do 4 tests on the 4 sides of the square, right? And the other thing that we need to worry about is this scenario where the line is shorter than the square. It could be inside of the square completely, in which case there won't be any intersection. Now, it's not sufficient to test if one of the points is inside of the square itself, right? Because if I have this picture, then it's going to say, oh, no, that's not, there's nothing, no obstacle in this cell, because this point is outside of the square, this point is outside of the square, right? But it's still, it's going, there's still an obstacle going through this environment. So
the goal is just to check if there's an obstacle in the cell.
yes, that's the whole point of the quad-tree decomposition algorithm.
Or maybe we can accumulate all the pixels in the cell, and if it's other.
That would be very inefficient if you have them as a line.
But the line will like only the pixel will have high number in the line, right? I mean, if like the line is blue, and we're going to check the blue channel, how's the accumulated?
I could do that, but then if I have a 4K image, I have to look at all 16 million pixels. Whereas if I have 10 lines, I just need to intersect lines.
Oh, I see.
So it will run much, much faster. There will be, if you have the obstacles given as lines, then it doesn't make sense to convert them to a bitmap and then check the bitmap for if there's any blue pixels in there. We could do that. I could do that for this scenario here. That's what I would have to do. Right? Here, I have no other choice because I don't know where these things are. Like Blender, I could print them out with Blender, but in this case, probably you wouldn't want to. You would want to just use it as a bitmap. But then you would make a much smaller bitmap, and then each pixel would correspond to the minimum cell that you're willing to generate. Because you clearly can't make it any smaller than 1 pixel. That automatically would limit the quad-tree decomposition. So Now we have to check if line intersect if the line intersection from CX to CY to CX plus CH, CY for the line x1, y1, x2, y2, if that is true, then the cell is not free. And we can break out here, yes. Else if the line intersection of CX to C, oh, it shouldn't be CX, CA, it should be C width. Plus CH. So then this would be CX plus C width. CX, CY plus CH. CX plus C width. CX plus C width. And CX. Yeah, no. CH plus CY plus CH. CY plus CH. Here we have CX plus C width. CX plus C width. All of those, then we break out, it's false. And otherwise, it is free, so we don't need to do any break anymore. So now I need to implement line intersection. How do you implement the line intersection? Intersection, and this is not line 1, this is L1x, L1y. Okay, we can do that. Line 1, 2. So here's line 1, line 2, and then L1 start is L1 end. L2 start, L2 end is there. Now, the line 1 is always going to be either a horizontal or vertical line in the particular algorithm that I have, right? So we could actually use a special purpose line intersection routine to only calculate the intersection between horizontal and vertical lines. And that would work. Or I could just use the general purpose line intersection algorithm, which will allow us to calculate any line segment intersections. But actually, calculating the line intersection is not trivial. Like, you're better off to look this one up. Even though I like to develop algorithms from scratch, this one is a little bit tricky. You need to calculate the determinant. Basically, what you need to do is you need to solve a system of linear equations, right? So the first line is going to be x, y, that point, plus, and then some k multiplied by x diff y diff. I guess I can write it in matrix form. That's the equation in matrix equation for our first line, right? For some k, where k ranges from minus infinity to infinity, because here we're dealing with lines at the moment. Afterwards, we have to check to make sure that it's, or actually, what would be the valid ranges for k? In this formulation where I just write it as x2 minus x1, y2 minus y1. And the line, it goes from x1, y1 to x2, y2. Right? Then any point on the line will be well, any point on the line will be a point where k is equal from 0 to 1. Right? Because if it's 0, then we're at x1, y1. If it's 1, then we're at x2, y2. Okay. Line 2, x dash 1, y dash 1. Similarly, right? This will be k1, this will be k2. X dash 2 minus x y dash x dash 2 minus x dash 1 y 2 dash minus y 2 y 1 dash. Right? So those two lines now are intersecting if correct, yeah. There has to be a point that's the same, right? So that means this and this have to be equal. And not only does it have to be equal, but also it has to be such that k1 is between 0 and 1 and k2 is between 0 and 1. Because when you're dealing with line segments. If you're dealing with infinite lines, then just any k that matches will do. So now we have a system with two unknowns and four equations. Yeah, so we have now a system of linear equations with four equations because I have I have this one, this one, this one, and this one, and two unknowns. So we need to find a solution to that system of linear equations. So let's write that down. x1, x2 minus x1, y1, minus, because I have x2 minus x1 multiplied by k1 minus plus. So I bring this home, I get k1 and it should be minus x2 dash minus x1 dash. K1, K2 is equal, and then here we have the constant part, so the constant part would be x1 minus x1 dash and y1 minus y1. Yes, we only have two equations, not four. Two equations. Because this one will be combined with this one because we set them equal. So we have two equations with two unknowns. That makes more sense. So we get x1 minus x1 dash, and this one will be y1 minus y1 dash. And the first one will be x2 minus x1, negative x2 dash minus x1 dash. And the next one will be y2 minus y1 minus y2 dash minus y1 dash. So if I multiply that out, I should get exactly the same. So we get k1, x2 minus x1, is this part here, minus x2 dash minus x1 dash, which would be this part here. So k1 multiply k2 would be equal to x1 minus x1 dash. x1 minus x1 dash, and then here we have y2 minus y1, y2 minus y1 minus y2 dash minus y1 dash, which is this part here, which will be equal to y dash y1 minus y1 dash, y1 minus y1 dash. Okay, so we have that. Now what? Now we have a system of linear equations with two unknowns, two equations. One way of solving that will be what's called Cramer's rule. And you probably heard about that in high school. How does that work? The determinant? Yeah. No, I think, isn't it like K1 would be equal to the determinant of replacing this? So that would be x1 minus x1 dash, y1 minus y1 dash, negative x2 dash, negative x1 dash, negative y2 dash, negative y1 dash, divided by the determinant of the original thing, so that would be x2 minus x1, negative x2 dash minus x1 dash, y2 minus y1, this is x not y, negative y2 dash negative y1 dash, and that gives you k1, and then you get k2, which now, instead of replacing the first column, we replace the second column. The other thing then you need to do is you need to watch out for making sure that the determinant actually exists, right? That it's not zero, which means that that matrix has to be non-singular. So there's a couple of extra tests you need to consider if you. So the usual implementation actually calculates, far as I remember, I think we calculate the first derivative. Sorry, the first unknown. Once you have that, you can actually just plug it into the equation here and then simply solve for K2. So you don't need to calculate 3 determinants. You can do it by calculating 2 determinants and then doing the division, which doesn't really give you that much extra power. But okay, and then how do we calculate the determinant? Yeah, so for 2 by 2 matrix, it's easy, right? A, B, C, D. The determinant of this is A times D minus B times C. And then if it's more complicated, if it's a 3 by 3 matrix, then it's even more annoying. Then you have to substitute and apply this plus minus pattern.
I remember there's a way to downgrade to 2 by 2.
Yeah, you do that. If it's a 3 by 3, you do the same thing, basically recursively. So I think if it's A, B, C, D, E, F, G, H, I, then I think it's, you cut this one, and this is plus, minus, plus, minus, plus, minus, plus, minus, plus. So you get plus the determinant of EF, HI, minus the determinant of DG, DF of DF, GI, plus the determinant of DE, DH. So that's, luckily we only have to do it here. If you need to do the 3-dimensional line intersection, then that's what you would have to do. So this is pretty pretty complex algorithm to get right the first time. So what does ChatGPT tell me? So the determinant is, it calculates the determinant of x diff and y diff. X diff and y diff. So it's trying to calculate that for this part here. X2 minus x1 x2 y. Yeah, so this is actually correct, right? Except I have the sign wrong. Because I have a negative sign here. If you look at the code that ChatGPT proposes, then it would be x diff, y diff there. So I think that just means that for K2 then, it needs to check if K2 is between -1 and 0 rather than 0 to 1. I think that's the only difference. Or it just swaps the start and the end points of, that's okay too. So then if the derivative, if the divisor is 0, if the divisor is 0, then we throw an exception. So I don't want to throw an exception. I just say that there's no intersection, which would be good enough, right? Like, why would you throw it? Not every line must have an intersection. So, I just set the intersection point to be this. So L1 start 0, L1 end 0, L1 start 1, L1 end 1. No, that is. Yeah, that's not right. Because here that shouldn't be x diff y diff. Determinant of x diff is, it shouldn't be x1, it should be L1 diff, alright? The difference in the L1 line and the difference in the L2 line. And this is line 1 start 0. Line 1's end 0 minus L1 start 0. And this one would be L1 end 1 minus L1 start 1. Right? This would be x minus x2 minus x1. Yep.
If you try to assign a variable called x and give it a value of 0, then you can read the code much easier. Just like x.
Oh, see, now it writes it correctly. After I wrote it there, so I have x1, what did I call it? x1, x1, y1 is equal to L1 start.
Yes, just like that.
And x2, y2 is equal to L1 end. And then I call them x1 dash, y1 dash is equal to L2 start, and x2 dash, y2 dash is equal to L2 end. Then x diff is equal to L1 diff is equal to actually that should be L1 end minus L1 start. That's all I need there, and this should be L2 end minus L2 start. And line 1, so 4 numbers. L2 start, L1 start. figured that one out, that I need to convert them into NumPy arrays. Then I can do this minus here. But then I cannot do this part now, because I cannot split the NumPy array along the columns.
Do we need to do so?
Hmm?
Do we need to do so, right? Because we already use the to implement the subtraction. So why I suggest that is because we need to implement the function to actually just all these variables.
Yeah, yeah, sure, but still, I still think we need this. We need these as NumPy arrays. So I can do this. Now I have the diff, and then I can calculate the determinant of L1 diff and L2 diff. And then if the difference is 0, then we return none. If the determinant is 0, then we return none. And other than that, so then we calculate the determinant, D, oh, now we can find the point that is, but it wouldn't be x1, x and y, it would be determinant of the line. I think that's wrong too. I will have to calculate the determinant of the line. This is not the determinant of the line. Star line 1. No, it will be determinant of, yeah, no. I think that is not quite right. Here, that should be that determinant. And it wouldn't give us x and y. Determinant D, x diff, determinant of D. So that doesn't even compute because D is a number, is a scalar, right? It's a single number here, so I cannot put it into matrix function. So this is like ChatGPT, quite often almost correct, but totally wrong. It looks correct, but it's actually wrong.
Illusion.
Yeah.
We have to put another row time to figure out.
Okay. No, you can just write it here then. Well, if you have that point, you're done. Right? There's nothing else to do anymore.
Yeah, but I mean, line 1,
because that's the y-intercept that has to be what you're saying,
I mean,
which is not true.
I mean, I assume these two lines are related.
Okay.
Without knowing, yes, and then calculate yes.
No, that does not work because here, this is a parameter, right? This y is not the same. This is y1, this is y2.
Yes, but we have to figure out this x, y, and then these two y are like the same one to find the intersection.
Oh, here, yeah, you have the y-intercept there.
These two are
Yeah.
on the line. And I figure out the x and then substitute back into the equation one to figure
Yes,
out
yes,
the
yeah.
and then
That's basically doing this.
But the second step is to calculate the distance with the rectangle. Manhattan.
The right angle triangle distance.
Yeah. And then just calculate the distance. So if the distance between this point and this point is larger than the distance between this point, then I know the intersection to be smaller than
Okay, so we have a1 x plus b1 is equal to x2 plus b2.
So I assume that x1 and x2 are the same x, which makes sense the x
Is it the same x?
yeah. Find the x first.
And then what we're getting is that b1, b2 minus b1 divided by a1 minus a2. That is x, right? Now that would be
That would be the x coordinate of the intersection point.
but then we have to calculate these b's first, right? We don't have those.
Yes.
So we have to calculate those first from x1, x2. So
Yes, because
so this is not going to work for vertical lines
yes,
because we cannot represent those at all. And then I think we have to basically do the same computation in order to figure out what b1 and b2 is. Once we have that, then we can calculate x. And then you're saying that this point has to be between this point has to, there's another thing too, so what happens if the lines are like this? One horizontal line is like that, and the other line is like this. Then actually there's infinitely many intersection points.
yeah, we can check the slope of these two horizontal lines before we calculate the coordinate. So we can compare the A1 and A2 to make sure they are not
But that's what I mean. There's a couple of special cases to worry about with like just implementing that is not sufficient. Um, you needed to check if the determinant is non-zero, and then I think you also needed to check for this because otherwise, I'm not sure what you would expect your algorithm to return. And but this is a neat idea. So you basically want to make sure that that point is between the minimums of x and y for one of the lines. Then, both of the lines. You have to test both of them.
But the one line is the boundary of the and another one is the optimum. So I can just test the boundary one to make sure that the point is on.
No, I don't think so because
Two.
if line 2 is like this, then the intersection point would be okay for this one, but not for this one.
Very nice. Because this comparison is much simpler by just subtract calculate the difference between the x coordinate and y coordinate.
Calculate the
Yeah,
difference
because
between x.
we don't need to calculate the degree distance, but the Manhattan distance. Like just count the pixel number.
You of course, yes. We could have optimized it by just knowing that one of the our quadtree decomposition is always going to be accessible, and that makes it easier. This one will be the general solution for any kind of line intersection, and I only wanted to show that basically because it seems so easy, and you have to do it all the time in computer graphics, and I always forget it, and basically end up looking up the algorithm because there is a couple of special cases that we need to worry about, edge cases. So let's just see. And ChatGPT also doesn't know how to implement that. So let's just see what the Wikipedia says. So they have one label. Okay, so here we have what I did. Except K1, K2, we have T and U. This is your approach, given two line equations as slope intersect format. Using homogeneous coordinates, we can do it using the cross product. So they also use Kramer's rule. No, that's not the. Here they don't actually calculate the solution, they just return true or false depending on whether they intersect or not. That, I think, since we go through all that trouble of doing most of the calculation, might as well calculate where they intersect. Okay, yes, this is the one. But I need it as arrays. A1, A2, B1, B2. So this is actually easy. The line intersection. One smaller one. Into star into. And then I need them all as numpy arrays. And then E is equal to O2 minus O2 star. DL1, DL2, DA is L1 start minus L2 start and DL1 and the denominator two and DE. But that doesn't check if they intersect. DL2 log log plus O2 start plus num line intersection I1 2. So then I want to say if not cell free, if it's not if the cell is not free, then we need to split it up. So the center point then would be for our nx ny would be cx plus cy. New width, new height would be new width divided by 2. And then I can call that quadtree decomposition on pass in the cell, and we want to generate a tree. And there should be 4 here. So cx, cy, new height, new width. No, new width, new height. Cell is 0, 0 height width. Okay. So then it should be cx, cy, c height, c width. So then better swap PDL. cx, c height, c width. And that's the cell. So here I implement my base case. So if the new width is greater than 10 centimeters and the new height is greater than 10 centimeters, or let's call that cell limit. And we generate the 4 trees. And I'm going to return children is an empty list, cell limit. is 10 centimeters, let's say. And then the first child is from CY, CX to new height, new width. If C1 is not none, then we append it. Then C2 is the next quadrant, which is CY, CX, CY plus new height, CX. If C2 is not none, C3 is quadtree of the environment for CY, CX plus NW, NH, NW. If that's not none, then we have a child that we append, and C4 is equal to quadtree environment. CY plus NH, CX plus NW, NH, and width. And if that's not none, then we append it. So what I want to return is my cell, which should be CY, CX, CH, CW, CY, CX, CH, CW, and children. And then if I have children, it's not free. If the set of children is empty, then it's a free cell. So then I want to take that and draw the quadtree, because otherwise it's a little bit hard to debug, right? So I can pass in the environment, can pass in the axis, the environment, and the quadtree. And then what do we need to draw? So first I want to plot the environment. Draw environment, we'll do that, right? Draw the environment. And then for if quadtree is not none, CY, CX, CY, CX, CH, CW children is equal to the quadtree. And then if children none, and the length of the children is greater than 0. Then the color is equal to gray, black, else color is equal to blue. And now we have to plot our tree. So that means AX dot plot. And that would be oh, I could do that. Just no, I don't want to. I need to plot all 4 lines, not just 1 line. First line horizontal, so that would be CX, vertical, CX, CX, CY, CY, CY plus CH, color is equal to color. Line width is equal to 2. So 4 lines we have to draw. There should be CX, CY here. CX, yeah, CX, CY. Should be CX, 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 CX. So CX, CX to CX, CY plus CH, then CX to CY to CX plus C width, CY, then CX plus C width plus C width, and it should be CX, CX plus CW, CY plus CH. Okay, it should plot it. Draw plot tree. Invalid syntax. Oh, so then let's see what we get. If we call plot tree decomposition, plot tree environment and cell, see if we can print it. If line intersection CX, CY. Oh, where did mass goes? Oh, um, line intersection CX, CY, CX. X1, Y1, X2, Y2. Line intersection returns, doesn't return a boolean, but returns an array. And then, so, is not none. Pprint. Pprint. Ah, oh no, I redefined my function. So that's not so good. I'll need to get this back. And that's probably why it's not, always a good idea to not redefine. Redefining is a bad idea, right? Because now I have a variable called quadtree. So it's much better if your functions always have some verb plus noun, like calculate the quadtree. Then you know it's a function. Whereas quadtree should be a variable, right? Is a noun. So it's I always like. I think it's a good naming convention to have some verb plus a noun if it actually is a function or something you can call. Whereas noun are reserved or should be used for variable things that you can actually modify. Objects if you want to. And now I have something. Who knows what? And this should be called quadtree. Ah, uh, so let's see what we get when we draw it. how can I even draw that vertical? The how do I CX CY? Oh yeah. So yes. So it should be CX CY goes there because it's X coordinates and the Y coordinates. So CX plus CW CY CX plus CW CY CX plus CW CY, maybe like that. Yeah. CY plus CH. Okay, so now we have everything blue and everything subdivided. So that's wrong. Oh, let's try. Um, okay, let's take environment 0, environment 1, and an empty list. So now we have an environment without any obstacles. Now what does it return? 0034 and empty list. So that's actually correct. So now let's put an obstacle, a line here, and the line should be the lines, I'm not ready for the lines. The lines are X, Y angle and length. So let's say X, Y angle length. So let's say 0.1 or 0.1, 0 degrees, and 1 meter, and that's the only obstacle. So then we have one split. I think our split is not correct. Oh, 0, 0, 3, and 4. So the next one is 0, 0, 1.5, 2.0, okay. And there is definitely a problem with our line intersection algorithm. That part actually should. It's not done at 0, 0, but put it at the end, so that should be. Is 3. Oh, and it's height and width. 2. Actually, 3.8. And 2.8 and 1.5. Oh, and then it goes. Take that one as 2.5. And the length will be 2. So 2.6. Angle 0, length 1. So that should be from 2.1 to 3.1. So that should be okay. Yeah, this all splits it up here into 2 small cells. So that the line intersection returns. The problem is this one here doesn't return. So there's a problem with the line intersection over here. So let's see. Section from 0.00 to 0.1. And then from 0.5. I think the problem is I missed up the 0, 0 to 0.1. This actually intersects, so this is correct. But I think I have the lines wrong because I have XY, but I expect YX. Yeah, so we'll have to change that. Anyway, that's it for today. We're running a little bit late. And then class for today. Yeah, see, so the obstacles are x, y, and the cells are y, x. Which is also cx, cy, c width, c height, and then we have to change all the intersection calls, the new calls for the quadtree decomposition. So cx, cy, new width, new height, cx, cy, new width, new height, cx plus new width, cy, new width, new height, c x plus new width, cy plus new height, new width, new height, and then when I set it up, it should be width height. But it still splits it into too many. Zero, zero, 3, 4, split, 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 split. But that's clearly incorrect. I could even try and set this environment, this obstacle, to be -10, -10, length of 1, so that should definitely not intersect with anything. It still splits it up, so the line intersection is not working correctly. So you can debug that until next class. Okay. And we're done here. And next week, we have another class with the German students. Have you talked to them? You're in contact with them? You?
Yeah, I think that they are not really charged at all for test.